right, hey y'all. It is time to talk about decomposition reactions. I think out of the 5 reaction types, this is my favorite. I might have said that about synthesis, but I mean it this time. I really love decomposition reactions. I think they're a lot of fun. And if you are tuning in and you're one of my students, or again, you are maybe a high school chemistry student, your teacher may have given you something like this at the beginning of the year. My students, it's in your reference table packet. And this is the section we're going to be looking at today. This is going to walk us through all the types of decomposition reactions, and we are actually going to do 5 different types today. They're all different, so you need to make sure you watch the whole video through so you know how to handle any reaction that you get. So have that handy, and it never hurts to have some sort of periodic table handy where you know the charges of your ions. Most of you probably already know these because you've used them so much at this point, but just in case, have that in front of you as well. So a decomposition reaction is basically where you have one reactant, and remember, reactants are on the left-hand side of the equation, and that one reactant breaks down into 2 or more substances. Here you see 2, it could be 3, it could be 4, usually it's 2 or 3 for beginning chemistry. So your big clue is you only have one reactant. You're only going to have one thing on the left side of the arrow. And just to give you a little bit of a refresher, I want to make sure you understand the difference between synthesis and decomposition because they're just opposites. Synthesis is where you are putting 2 or more things together and getting one product. Decomposition is where you have one reactant that is decomposing into 2 or more substances. So you can see they're just mirror images of each other. Before we move on, real briefly, you know, what causes a compound to decompose? Like, what would even make that happen? Some really common things could be heat, light, specifically sunlight, electricity, and time. Just like us, we get old and start to fall apart. You probably hear your parents say that from time to time. Some compounds get old and they kind of fall apart, and we call that decomposition. I've got a couple common examples for you, just some things that you'll see and say, oh yeah, I knew that. I just didn't know what kind of reaction it was. Airbags, and these are some of the older airbags. I believe they've changed the technology and the chemistry, but the older airbags used something called sodium azide. That was a solid substance, pretty stable unless it's exposed to heat or maybe an electrical current, little jolt of electricity. And what would happen is was in the airbags, and I believe in automotives, maybe a spark of electricity is what set this off, but it would break up very quickly into sodium metal and nitrogen gas. That nitrogen gas is what fills up that airbag so quickly, and anyone who's ever maybe been in an accident where you've had an airbag deployed, and you know it happens super quick. And just as quickly as it happens, there were little holes in the back and it would start to deflate, so you didn't feel like you were hitting a brick wall. But that's just a little common chemistry that you may be familiar with. The carbonic acids in sodas, H2CO3, that will break down into water and carbon dioxide, and that carbon dioxide is your fizz. Sometimes you hear that little sound when you maybe opened up a canned drink or a bottled drink. And then hydrogen peroxide. Lots of you have probably used that maybe on a cut or as a disinfectant to clean out a cut, and that is H2O2. It's almost like water. It's just got that extra little oxygen hanging on, and that oxygen is not held on very tightly. That is why peroxide is in a brown bottle. This is easily decomposed by sunlight. That's going to speed that process up. So when this is exposed to sunlight, and I believe it's also maybe an enzyme that's found in your blood, it's going to break apart into hydrogen gas and oxygen gas, and that bubbling that you see when you pour it on a cut is that extra oxygen gas that's breaking apart from the water molecule. Actually, that breaks up into water and oxygen gas. So not hydrogen gas, it's water and oxygen gas, I believe. So just some good everyday examples of some things that you may see decomposing. Another one is the electrolysis of water. That's where you can run an electrical current through a water molecule and it will break up into hydrogen gas and oxygen gas. So just some things to be thinking about as we run through this lesson. Now, the goal of today's lesson is if I give you any reactant, you should be able to identify what type of reactant you have, and then you should be able to predict the products that you're going to get from that reactant. So again, we're going to be very, very dependent on this page from our reference table packet. If you're a college student, chances are your professors probably want you to have this memorized, so you probably would just have to know this for a test. Most high school students, it is given to you. So you're going to see me pull this in a lot. The first type of decomposition reaction that we're going to talk about is decomposition of a binary compound. And this is just where basically you have an ionic compound and it breaks up into the metal and the nonmetal. And when I say ionic compound, it is binary. That means it does not contain a polyatomic ion. Those have to be treated differently. It is just simply a metal and a nonmetal. So we might want to make a note there. Binary ionic is metal, nonmetal. Once we get to the polyatomics, we're going to handle those just a bit differently. So these are actually super easy because it's almost like you're just uncrisscrossing them. So think about the two things that make up barium oxide. You have barium, which is just a metal, and then you have oxygen. Now here's where you've got to be careful. Oxygen is one of the special 7 diatomic molecules right here, okay? Plus we throw hydrogen into the mix if you remember that. These can never exist alone. If you write them alone, they at least have to be bonded to their clone, so we have to put a 2 on it. I always say, Beyonce would say, put a 2 on it. Now, number 2, potassium iodide. That is made up of potassium and iodine. Again, I see one of the special 7 diatomic molecules, and we're going to put a 2 on it, just because iodine is one of those 7 that cannot exist alone. Number 3, magnesium chloride. That is made up of magnesium, and it's made up of chlorine. Again, chlorine is one of the special 7 that cannot exist alone. It is diatomic, so put a 2 on it. You will get used to very quickly when you write these, if you forget to put the 2 on one of the diatomics, it's going to look strange to you. So that's something that students are typically very good at very quickly. Number 4, lithium sulfide. That is made of lithium and sulfur. Now, sulfur is not a diatomic molecule. It can actually exist just like that, so we're done. We do not put a 2 with the sulfur in this case. So what you can see, a couple things I just want to point out, is all of these are just simply a metal with a nonmetal. You don't see any polyatomic ions, and it's almost like we're just taking that ionic compound and we're plucking it apart. You're just pulling it apart, but you're being really careful if it's diatomic to make sure you put a 2 on it. So something you may want to do is jot down these last 4, try them yourself, and then as I go over them, you can make sure that you've got this concept before we move on. Barium fluoride will break up into barium and fluorine gas. Fluorine is special, it gets a 2. Aluminum oxide will break up into aluminum and oxygen gas. Calcium sulfide will break up into calcium, and sulfur. We do not put a 2 on this because it is not a diatomic molecule. And then we have the last one, sodium phosphide. That will break up into sodium and phosphorus. Phosphorus is not diatomic, so we do not put a 2 on it. So I think probably before we move on, I would definitely make a note to be careful with your diatomics. These will come up a lot in a lot of different types of chemical reactions. And if you want to list them just to be on the safe side, your diatomics will be nitrogen gas, oxygen gas, fluorine gas, chlorine gas, bromine gas, iodine gas, and hydrogen gas. You've got 7 of those, so just watch out for them when you're writing your chemical reactions. So you might want to make a note of that before we move on to the next page. So binary decomposition are simply a metal, non-metal combination. You literally just pluck it apart, being careful to put a 2 with any diatomic gas. Now I do want to point out too, these are not balanced. We are just today focused on predicting the products of the reaction. When we are actually using these in other problems, we'll be sure that we balance them first. But for right now, we are simply just writing down the chemical formulas. All right, sorry, pardon the doorbell. It looks like our UPS man just dropped off a package. All right, continuing on. It never fails. As soon as I sit down to film a video, I get company. All right. Now let's talk about the decomposition of metallic carbonates. These are where you're going to have to start really paying attention to detail. They're not hard, you just got to pay attention. So here's what I want to point out about a metallic carbonate. The packet tells us this. What I want you to do is look at what I'm pointing at and listen to what I'm saying, and I'm going to kind of tell you, if that packet could talk to you, what would it be saying? So here's what the packet says. If you have any metallic carbonate, that M could be any metal, I want you to crisscross that metal with oxygen and add CO2. So whatever this metal was, crisscross it with oxygen, which you know has a -2 charge, and then add CO2 as a byproduct. That's all you do. So all of these examples are metal carbonates. You can see I've got metal carbonate, so on and so forth. So it's important that you know that carbonate is CO3 minus 2. That is a polyatomic ion. And a metallic carbonate is just any metal that is crisscrossed with that carbonate ion. All of these are metal carbonate, metal carbonate, metal carbonate. That's how you recognize them. So they're really easy to pick up on. Now what we want to do is go through and predict our products. So number 1, we have aluminum carbonate. Now the metal in this is aluminum. So according to the rule, we're going to crisscross that metal with oxygen. So I'm going to crisscross this aluminum with oxygen, and then I'm going to add CO2. And if somebody asks you, why did you add CO2? Just say the packet made me do it. Literally, that's the rule. So I'm going to do my scratch work. So I'm switching to a smaller marker here. I'm going to do my scratch work above. So I'm going to crisscross aluminum, which has a +3 charge, with oxygen, which has a -2. When you crisscross those, you get Al2O3, and then you add CO2 because that is what the rule tells you to do. So when aluminum carbonate decomposes, you get aluminum oxide and carbon dioxide. Let's look at the next one. We have magnesium carbonate. Here's my metal. So I'm going to crisscross that metal with oxygen, just like the rule tells me to do. So you get these together by crisscross, okay? So magnesium is a +2. Oxygen is a -2. The 2's actually cancel out, so you get MgO, magnesium oxide, plus carbon dioxide. Again, you add that because the rule simply tells you to do it that way. Number 3, sodium carbonate, and that is actually wrong. There you go. Ca2CO3 is what that's supposed to look like. Sodium carbonate decomposes, so there's your metal. Sodium has a +1. Oxygen is O-2 because according to the rules, I'm crisscrossing the metal with oxygen. So that is sodium oxide plus carbonate. So what you can see here, the trend is you look at the metal that was attached to your carbonate, you take that metal, crisscross it with oxygen, and then you just add CO2. Let's look at number 4. I have iron carbonate, but that iron is a transition metal. So I've got to figure out what the charge of that iron was before it was crisscrossed. I need to know that so I know how to crisscross that iron with oxygen. Now, carbonate has a -2 charge, and it's in a 1-to-1 ratio with this iron, so that tells me that this iron was a +2, and I'm just going to make a note of that right there so I remember. So this was actually iron 2 carbonate. That's important because when I crisscross the iron with oxygen, I want to make sure I'm using the right one. Those 2's cancel, so you get FeO plus CO2. So I would just tell you to be careful with any metals that are transition metals because you know you have to think just a little deeper into those. Let's look at the next one. I've got copper something carbonate. Again, I have a transition metal here, so I need to know which copper that was. Now this 2 came from here, and that makes sense because carbonate does have a -2 charge. So that means this 3 had to have come from up here. So this was actually copper 3. So I'm going to make a note of that. Now I'm going to crisscross the metal with oxygen. Put my scratch work up here. Copper +3, oxygen's a -2. When you crisscross, you get Cu2O3 plus carbon dioxide. Why? Because the rule told me to do it that way. Potassium carbonate. I'm going to crisscross this metal with oxygen. Potassium has a +1. Oxygen is a -2. That is K2O plus CO2. And the last one, barium carbonate. That makes sense because barium's a +2, carbonate's a -2, so it makes sense they would have canceled each other out, and that's the way it should look. That's not a transition metal, it's just a plain old metal. So I'm going to crisscross barium with that +2 with oxygen that has a -2. That is BaO because the 2's canceled plus CO2. So the name of the game with a metallic carbonate is to identify your metal and crisscross that metal with oxygen. That's all we do. When we take that metal, make a little note here, the metal with its positive whatever charge, and you're going to crisscross it with oxygen. That's the first step, and then the second step is add CO2. That is how we predict the products for a metallic carbonate. And the rest of the polyatomic ions we're going to look at for decomposition, you're basically doing the same process. You just may be crisscrossing with something different, or you may have different byproducts. But we're going to use the same sort of format. So now let's look at the decomposition of a metallic hydrogen carbonate. So first of all, what we need to know is that hydrogen carbonate is HCO3 minus 1. That is one of our polyatomic ions. So a metal carbonate, or metal hydrogen carbonate, or metallic hydrogen carbonate, same thing, is going to be a metal that has been crisscrossed with hydrogen carbonate. So you can see right here, when we have a metallic hydrogen carbonate, we are going to crisscross the metal with carbonate, and then we are going to add water and carbon dioxide. So this is one we're doing a little differently, but we're still crisscrossing. So if you look right here in the reference packet, it tells us the exact same thing. When you have a metal hydrogen carbonate, crisscross the metal with carbonate, add water and CO2. So again, this is going to be a metal with whatever its positive charge is, crisscrossed with carbonate, which has a -2, and then you're just adding these two guys in because that's what the rule tells us to do. So number 1 is sodium hydrogen carbonate. I'm going to take that metal, I'm going to crisscross it with carbonate because that's what the rule tells me to do. So sodium is a +1. Carbonate is CO3 minus 2. Crisscross, that gives me Na2CO3. And then add water and carbon dioxide because that's what the rule told me to do. Number 2, potassium hydrogen carbonate. There's my metal. Identify that first. Now crisscross that metal with carbonate. That is K2CO3. And then because the rule tells me to, we are adding water and carbon dioxide. And I will tell you that water is a liquid and the carbon dioxide is a gas. And later on, when we get into some more involved chemistry, we'll actually label all those things as solids, liquids, gases. But right now, we are just focused on predicting the products. We'll put all the other little bells and whistles in later. All right, number 3, I have calcium hydrogen carbonate. Calcium is my metal. So I'm going to crisscross that calcium, which has a +2 charge, with carbonate. The 2's cancel, so that is CaCO3 plus water plus carbon dioxide. Number 4, lithium hydrogen carbonate. There's my metal. It's lithium. Lithium has a +1. Carbonate is CO3 minus 2, crisscross Li2CO3 plus water plus carbon dioxide. So if you know how to identify the metal, how to crisscross it with carbonate, and then just add water and CO2, that's literally all you do for these. They're very easy. This would probably be a good place to pause the video, maybe jot these down and try them. And then when I go over them, you can make sure you've got this concept before we move on to the next type of example. So number 5, aluminum hydrogen carbonate. Aluminum is my metal. Aluminum has a +3 charge. Carbonate is CO3 minus 2. Crisscross, I get Al2, then in parentheses, CO3, 3. That's aluminum carbonate plus water plus carbon dioxide. And the last one, cobalt hydrogen carbonate. But Cobalt is a transition metal, so I got to be a little more careful on that because I have to know which cobalt that was. Now, hydrogen carbonate has a charge of -1. This is in a 1-to-1 ratio with cobalt, so this cobalt must have also been a +1. And I needed to know that charge because I'm getting ready to crisscross cobalt with carbonate. So if cobalt has a +1, carbonate is CO3 -2. When they crisscross, you get CO2, CO3, make sure that's lowercase and uppercase, that could get kind of tricky, plus H2O plus CO2. And that is how you do the decomposition of a metallic hydrogen carbonate. So if you wanted to summarize this one down at the bottom, basically the first thing you do is you crisscross your metal with carbonate, and then you add H2O and CO2. And honestly, it does not matter the order that you add the H2O and the CO2. You could put, you could easily put CO2 plus H2O. This order does not matter, but you know, just kind of in the habit of doing things the same way. But if you see them switched, that is not a problem. All right, so we have covered decomposition of binary compounds, binary ionic compounds. That's just metal, nonmetal. We have covered the decomposition of metallic carbonates, a metal that is bonded to the polyatomic ion carbonate, and the decomposition of metallic hydrogen carbonates, which is a metal bonded to hydrogen carbonate. So now we're going to move on to another type of polyatomic ion. The good news is you're not going to have to learn this process for every polyatomic ion. Some of my students might have been shuddering a little bit thinking that was coming, but there's only a few of these we're going to have to do. And again, the good news is you don't even have to memorize it. All you have to do is look in your reference table packet, and there's the rule. So the next one we're going to look at is the decomposition of hydroxides, and it's of actually metal hydroxide. So add metal in there, metal or metallic, same thing. And this is simply a metal that is bonded to hydroxide, and hydroxide is one of our polyatomic ions. And what the packet tells us to do on the decomposition of a metal hydroxide is crisscross the metal with oxygen and add water. So whatever that metal is, we're going to crisscross it with oxygen, which you know has a -2 charge, and add water. So number 1 is potassium hydroxide. Identify your metal, which is potassium. Potassium is +1, oxygen is -2, because we're following the rule here, and we're crisscrossing it with oxygen. That is K2O plus H2O. Number 2, zinc hydroxide. That is a metal hydroxide. I'm going to identify the metal. Zinc has a +2 charge. I know that because I've memorized it. We're going to crisscross with oxygen, which has a -2 charge. They cancel. That is ZNO plus H2O. Number 3, this is iron 3 hydroxide. I know it's iron 3 because the 3 here had to have come from up here. So I'm going to just make myself a little note because that's a transition metal. Takes just a little more attention to detail. So I'm going to crisscross that iron with a +3 charge with oxygen, which has a -2 charge. That is Fe2O3 plus water. Number 4 is magnesium hydroxide. I know magnesium has a +2 charge. Magnesium has a +2. Oxygen has a -2. The 2's cancel. You get MgO plus water. And the last one, manganese 4 hydroxide. This is a transition metal. I know that 4 came from up here, so that was manganese 4. I needed to know that to crisscross it with oxygen. Manganese is a +4, oxygen is a -2. We have a little something special in this one. These two charges will actually reduce before you crisscross. That's going to reduce to a 1 and a 2. So it's going to be MnO2 plus H2O. So for metal hydroxides, you are going to identify the metal, you will crisscross it with oxygen and add water. So again, it's all about identifying your metal, being careful if it was a transition metal. You want to make sure you account for that. And then you are crisscrossing that metal with oxygen. So we'll make a little note about this one before we move on to our next example. So crisscross, I'm going to write this just a little bit different. Crisscross the metal with your oxygen that has a -2 charge. So basically whatever this is with this. And the next step is add water. And that is how you do the decomposition of a metal hydroxide. Now we have one more that we're going to look at today, and this is the decomposition of a chlorate. So let's take a look at the rules and see what they say. And I guess you're seeing, as long as you follow the rules, you do it the same for each type of polyatomic ion every time. So metal chlorates, that's where you have a metal crisscrossed with chlorate. Remember, that's your polyatomic ion, ClO3 - 1. The rule says crisscross the metal with chloride and add oxygen gas. So in this case, we will crisscross this metal. Go to a smaller pen here. The metal is crisscrossed with chloride, which we know has a -1 charge. We're going to crisscross those and add oxygen gas. So these are very straightforward. Chloride, or chlorate, pardon me, is ClO3 - 1. That is your polyatomic ion chlorate. All right, let's look at number 1. Sodium chlorate. Identify the metal, because our rule says take that metal and crisscross it with chloride. So the metal is sodium, Na+1. Chloride is Cl - 1. The ones cancel, NaCl plus oxygen gas. So for all of these, this time we will be adding oxygen gas. And again, it's because that's exactly what the rule told us to do. Number 2 is silver chlorate. Silver is our metal. Silver has a +1 charge. That's one of the exceptions that we memorize. Chloride is a -1. Again, the ones cancel. That is AgCl plus O2. And, keep in mind, all this stuff up here is just my scratch work. A lot of you could probably just do this in your head, but since we're taking notes and I'm teaching you this new concept, I like to write everything down. Number 3, copper 3 chlorate. I know this is copper 3 because this 3 had to have come from up here. So this was one of those transition metals that we have to pay close attention to. So I'm going to crisscross that copper 3 with chloride, which has a -1. That is CuCl3 plus O2. Number 4, this is lead 2 chlorate. I know it's lead 2 because the 2 had to have come from up here. So I'm going to crisscross lead with a +2 with chloride, which has a -1. That is PbCl2 plus O2. Number 5, aluminum chlorate. Aluminum is my metal. It has a +3 charge. Chloride is a -1. The rule tells me to crisscross that with chloride. When I crisscross, I get AlCl3 plus O2. And the very last one, copper 3 chlorate, which I noticed I've already done, so we're not going to worry about that one. That was a repeat. Sorry about that. So let's just talk about these real quickly then. As a recap, what you can see is on decomposition, if it's binary, and remember that is a metal, nonmetal, no polyatomic ions, you're literally just imagining grabbing that compound and just plucking it apart. Just be careful if it's one of the 7 special diatomics that you put a 2 on it, okay? If it is a metal combined with either carbonate, hydrogen carbonate, hydroxide, or chlorate, you're going to really need to focus on these special rules. Don't stress about it because they're right here in front of you, or at the very worst, if you're a college student, these are not hard to memorize. But this rule will tell you crisscross the metal with oxygen, then add carbon dioxide. Crisscross the metal with carbonate and then add H2O and CO2. Crisscross the metal with oxygen, add water. Crisscross with chloride and add O2. When you see these metals that you're combining with different things, I want you to think crisscross. You're just writing an ionic compound and then just add all of those other things, which we're going to call the byproducts, and it's no problem. So we're not going to worry about the oxy acids today. We will hit those in another lesson. I will go back on this one though and make a quick note. For the decomposition of a chlorate, or you could say metal chlorate, sometimes people don't put the word metal in front, I like to. The rules are, you're going to crisscross the metal with chloride, Cl with a -1, so it's going to be this and this crisscrossed, whatever that charge happens to be, and then the second step will be to add oxygen gas. So not hard. If you're a rule follower, you'll love these. If you're not, you'll get used to it really quickly. So decomposition covers a lot of ground. That's probably the longest video that we will have in terms of types of chemical reactions. Just keep in mind that decomposition is the exact opposite of synthesis. And your clue, again, is that you only have one reactant. So the next video that you're going to see is going to cover single replacement, then we're going to have double displacement, and then combustion, and that will wrap up our series on chemical reactions.